Hi class, we are starting a new chapter, chapter 4. This entire chapter deals with higher order DEs. So we are going to see the presence of second derivatives, third derivatives, nth derivatives, right, in our differential equations. So the methods of solving these are different than they are for a first order. Obviously it's a little bit more complex. So, we're not doing separation of variables, integration factors, things like that. They will pop up for certain problems. One of the main ways that we like to deal with higher order DEs is by what's called reduction of order, where we try to take a second order and make some sort of a substitution to make it a first order. And then we can solve it with our first order methods, right? Obviously, it doesn't always work. Like I said numerous times, there's several DEs that are not solvable, and then you have to use numerical methods. So we're really just going to go over the preliminary theory for linear equations, right? Because we can obviously have higher order DEs that are nonlinear, which require different approaches. So we're just going to talk about the basics of all the things you're going to see in this chapter, right? So this chapter is pretty long. It's 9 sections. If you're looking at a newer version of the textbook, it's 10. So for the students in my class, you'll see a few discrepancies in some of the chapter numbers. The label of your homework versus the video that I say that we're on, or the section that we're on. And that's because I'm using the 7th edition for this textbook. And for my class, this semester or in future semesters, the bookstore automatically kind of assigns the newest version, right? So the numbering may be off. If you're not in my class, if you're just watching this for your own purposes or for another class, you can disregard that entire statement. It doesn't even matter, okay? So we're gonna just kind of go into the introduction to solving higher order DEs, right? So we're not really going to solve anything, but we're going to talk about some of the components that we use when we talk about solving them, the way that their solutions work, some of the necessities that we need in order to find a solution, period, right? And some of the characteristics that the solutions take on. So start off with the theorem. Let a sub n of x, a n minus 1 of x, right, up until a1 and a naught of, then we have g of x, right? So when g of x is 0, that's generally when we're going to be in a homogeneous situation, and when g of x is non-zero, it's a non-homogeneous equation. So these are all functions that are coefficients for an nth order differential equation, right? Here a sub n of x is the leading coefficient, and it's attached to the nth derivative of y. A naught of x is the coefficient that's attached to just my standard function y, right? So it goes in order, decreasing in derivatives, as we've seen before. Here, these can be constants, which is what we're kind of comfortable with, but not always, right? We can have variable coefficients as well. We've seen that in chapter 2. So it's very, very possible that these are functions in x, right? When they are functions in x and y, or functions of y, that's when we are in a nonlinear situation, right? So let this DE be continuous on an interval, which we'll call I, right? And let the first term be non-zero, because if the first term is 0, then I now have this as my order, and that would be my a sub n, right? So here a n of x is non-zero. So not only that, but notice it's a function, right? So it needs to be non-zero over my interval of existence. Okay, so over the interval of existence, it's non-zero. Anytime that it is 0, well, you're then looking at sort of the boundaries of the interval that you're continuous on, basically, right? So if x equals x naught is any point inside of this interval, right? So this is my initial condition. My initial condition is picked to be somewhere inside of this interval of continuity and existence for my DE, right? X naught is inside that interval. Then a solution, y of x, right? This function I'm looking for, of this IVP exists on the interval and is unique. So this is our existence and uniqueness theorem for an nth order differential equation. Okay, so what is our condition? We're not looking at any derivatives. It's just that my first term is non-zero over some interval, and somewhere inside of that interval, I have an initial point. As long as those two things are true, then I have a solution, a unique solution that exists to this IVP. Okay. When we talk about boundary value problems, we already know it can have mixed results. We talked about that a little bit in chapter 1.1 video. I can have many, one, or no solutions for boundary value problems. There's no sort of conditions regarding solutions to those. Okay, so it's really a case-by-case kind of basis, right? Differential operators. So we talked again in chapter 1.1, right? So this 4.1 video is going to really be reflective of 1.1. 1.1 was just like an intro to DEs. This is an intro to higher order DEs. Higher order DEs is probably the most common thing you're going to run into, right? Rather, other than PDEs, partial differential equations. So we haven't really used the differential operator too much, so we're going to discuss it briefly, but it is going to come up quite a bit in chapter 4, right? So this is just an introduction here. An operator is basically just a function, okay? It's another name for function, although operators act on function. It's like a function for a function, right? When you differentiate something, you're differentiating a function. Your derivative is an operator on your function. It's a function for your functions. Integration is something you do to functions. Integrals are operators, okay? So things you do to functions are called operators, right? Things you do to inputs, to numbers, those are functions, right? You plug a number into a function, you get another number out. For an operator, you plug in a function, you get another function out. That's an operator, okay? So the differential operator D is a function basically where it differentiates the inputs, and what are your inputs? Your inputs are functions. So an example, if I'm plugging in x squared plus 1, we generally think of our differential operator as acting on x, right? Whatever the independent operator is, right? Or variable is. So the output for plugging in this to my differential operator, the operation onto this function is that it differentiates it, okay? Here, d of dy, so this differential is differentiating y, but y is generally a function of x, right? So this isn't going to turn into just 1. But if I multiply d times dy, or if I'm plugging in an operator, a function that I'm operating on already, it's like I multiplied the operators, okay? So I'm actually getting dy, or d squared y, which is the same thing as just the second derivative of y with respect to x, okay? So differential operators, you're familiar with how they work. It's just a notation you're going to have to get used to, okay? The next thing we're going to talk about is linear combinations. So the next, I want to say 4 things we discuss in this class, in this video. If you've taken a linear algebra course, you're going to be super familiar with the content we're going to go over, okay? If you have not taken a linear algebra course, I have a whole series on linear algebra. It may be above the level because by the time we talk about this stuff in that class, we've got a lot of foundation covered already. But this stuff is very, very important. The next few things that we cover is not just for linear algebra or differential equations. It's really the basis for a lot of higher order math. So a linear combination is basically a sum of functions, each of them being multiplied by a constant coefficient, okay? So it's basically a bunch of terms, just like a polynomial, just like we see here, where it's a function times a coefficient, right? So here, that's not what this is. It's a derivative times some function, but it's the same thing. This is considered a linear combination of some sort. It's not actually a linear combination. A linear combination is a constant times a function plus another constant times a function, and so forth until you run out of functions, right? So it's a constant multiple of a function plus a constant multiple of another function, where each of these constant multiples can be the same, they can be different, they can be any value, right? So if I add up a bunch of functions together and I'm scaling them by different values as I add them, I'm going to end up with a new function. So this function is a linear combination of other functions. Linear because none of these things are squared or square rooted or anything like that, even though the function itself may not be linear. This may not be a linear function. This can be a sine. This can be a cosine. This could be square root x. This could be x to the 12th power. It doesn't matter. It's just some function, but I am not doing crazy things to the functions themselves, right? I'm taking a function and I'm adding a scalar multiple of it and adding that to a scalar multiple of another function, so forth, so forth. But when I add them together, I will get a new function. It is a combination made out of other functions. Very, very important. This idea of linear combination, super important for the rest of the course. Very, very important in linear algebra. So let's say we have an operator, and we call it L. This is going to be considered linear if it satisfies the following property. Basically, if it is operating on a linear combination of functions, it's the same thing as a linear combination of the operator operating on each of the individual functions. Okay, so inside of the input of this operator is a linear combination. Alpha times a function plus beta times a function. Alpha and beta are constants, right? C1, C2 up to Cn, these are constants. They're real valued coefficients. So here I have a linear combination being acted on by an operator. It would be the same thing if I had a linear combination of my linear operator, right? So a constant times my operator acting on a function plus a constant multiple of my operator acting on a function, right? So again, if I plug in a linear combination into my operator, it will be the same thing as a linear combination of my operator acting on each individual function. Okay, so this is also a very, very important property which we talk about in linear algebra, right? We talk about transformations. This is extremely, extremely important property of transformations. It's literally the definition of a transformation for my linear algebra students or those who are taking it concurrently. Very important properties, right? So those all transfer over to differential equations, because differential equations, in all honesty, it's really just a lot of linear algebra, okay? So superposition, okay? This is also a property from linear algebra. We've seen this. We talked about it in chapter 1.1 a little bit. We're going to review it now because we are actually going to be using this property all over the place. So we talked about it in 1.1. I even showed you an example. However, we haven't used the property of superposition yet. We did use superposition in chapter 2.5. I think it was 2.5 for the exact equations of solving first order linear equations, although I didn't specifically tell you we were using the superposition property. So in 2.5 we were integrating with respect to x, we were integrating n with respect to y, maybe the vice versa, and then we would get one solution and another solution, and we just took the linear combinations of each solution to add together to make one full solution, right? That was the superposition property that we're using in order to form that solution from two separate integrals that we created, right? From the same parent function, I guess. Okay. So linear combinations of distinct solutions. So things that are non-repeated from one solution to the next solution to a DE are solutions to the same DE. So if I have two different solutions, but there's repeated terms in both solutions, I'm just using that repeated term once in my actual solution, right? I don't need it twice, because then I have a constant multiple of it, basically, and that's what the C1, C2, C3s are for, right? So if YG is a solution to a homogeneous DE, which we generally call, or what is called the general solution, and YP is a solution of the same DE when it is non-homogeneous, which we call the particular solution. So YP is the solution to a non-homogeneous equation. YG is the solution to a homogeneous equation, right? So this equation is the same equation. It's just that one has 0 on the end and the other one will have something that's not 0 on the end. Then the superposition of those two solutions is going to be a solution to the non-homogeneous DE as well, right? So an example, okay, because all of this might be like, Professor Williams, I don't know what the hell you're talking about, so we'll do an example, right? And again, if you're like, you can go back to the 2.5 video and you can see where I talked about this, but I didn't say the word superposition. But when I'm pulling pieces that are different from both the integrals that I found and put them together to form one solution, I'm using the property of superposition to do that, okay? So let's say we have a homogeneous DE, y double prime minus 7y prime plus 10y equals 0. It's going to have a solution of yg equals c1 e to the 2x plus c2 e to the 5x. Now you might say, how do I know that's a solution? Well, we're going to check. I'm just giving it to you, right? This chapter 4, is all about finding solutions to things like this, right? So if I want to check that this is a solution, obviously what I need to do is I need to find the first and second derivative, right? So the first derivative is 2c1 e 2x, 5c2 e to the 5x. The second derivative, I'm just doing that again, right? 4c1 e to the 2x, 25c2 e to the 5x. Then I can throw them all together into this DE. So I'll throw in my first term, right? My y double prime goes here. Minus 7 of these. Okay, and obviously I'm running out of room, so it's going to kind of wrap around over here. And then 10 of the YG solutions. And so when I start to add these together, you can see I got 4 C1E 2x's plus 10 of them is 14 minus 14. So that'll be 0, right? For e to the 2x. E to the 5x is here, here, and here. So I got 25. I am subtracting 35 and adding 10. So that's 35 minus 35, right? So, right, 25 plus 10 is 35, and then minus the 35. So 0 plus 0 is always 0, okay? So this is the solution to the homogeneous form of this problem, okay? For the non-homogeneous DE, y double prime minus 7y prime plus 10yc, same basic form. The only difference is that instead of it being homogeneous, it's non-homogeneous, right? The solution to this DE is this equation, okay? So just by changing this to 0, look how different the forms of my solution are. This has two pieces with C1, C2. They are it's a whole family of solutions. There's an infinite number of solutions that satisfy this. Here, there's not. Here, this particular solution is one single function, right? So if I plug that in here, okay, so notice that no matter what derivative I take, I'm still going to get out 6e to the x, right? Because it's just the one that keeps coming down here. So very easy to differentiate this function. So when I plug it in and I take my second derivative minus 7 times the first plus 10 times the original function, I get the following, right? So when I add these together, okay, 66 minus 42 is going to be 24 e to the x, right? That would not be the same if I had a constant multiple here, right? If I had C1, C2, and C3, or what have you, right? So here, my particular solution is very, very direct, okay? However, we're using this property of superposition. It says that if I add these two solutions together, I'll still get a solution to my non-homogeneous DE. So that's what we're going to do, okay? If I add my solutions together, I get a family of solutions because I have these two variables plus this particular solution for the non-homogeneous portion. The derivative of y will be 2c1, 5c2e to 5x, 6e to the 6. The second derivative is very straightforward. It's really just me adding those two second derivatives together, okay? When I plug this into my DE, right, I'm plugging in y double prime minus 7y prime plus 10 times my y function. And instead of just like going all willy-nilly and simplifying this, to show you what's happening here, I'm going to separate this now to all the C1, C2, e to 2x, e to the 5x parts being plugged into y double prime minus 7y prime plus 10y prime, which we actually know is already 0. Okay, so what I'm doing is I'm just separating this out. I'm basically factoring out all the e to the 2x and e to the 5x stuff into my general form of my dE. And I will add to that the same thing, but with my particular solution being plugged in, right? So I know that this adds to 0, because we just did that. And I know that this adds to 24x, because we just did that, right? So my superposition of my general solution and my particular solution will always form a solution to my non-homogeneous dE. Very, very important. We're going to talk about that for a lot of this chapter, chapter 7. Okay, so notice that I went from going, oh, I have only one single solution to the non-homogeneous, to now an entire family of solutions to my non-homogeneous dE. Okay, so a set of functions, f1 of x, f2 of x, and so forth up to, so forth up to f sub n of x, is linearly independent. So again, we've been talking about superposition. Okay, we've talked about linear combinations, differential operators, and linear operators, right? So the differential operator is actually a linear operator as well. There's several linear operators. Okay, operators are very important. There's actually whole classes, whole areas of math focused on operators. It's called operator theory, and all it is basically the algebra of operators, right? Nonlinear operators and operators alike. Very important for things like quantum mechanics, Hilbert spaces, those higher order sort of things that you study in physics and in mathematics. Okay, so let's talk about linear independence, which is very, very important as well. This is also something that comes out of a linear algebra class, right? That's applicable to a DE course as well. So these functions are linearly independent if the homogeneous equation formed of their linear combination has only the trivial solution. Okay, so let's think about this before I show you what that means. If the homogeneous equation formed of their linear combination, so basically if I add these things together as a linear combination, c1 f1 of x plus c2 f2 of x, so forth and so forth up to cn times fn of x, is homogeneous. So if that linear combination is 0, has only the trivial solution, then it's going to be linearly independent. Now the trivial solution, we discussed this again a lot in linear algebra, somewhat in diffuse. Trivial solution means the easiest solution to this question is the trivial solution. It's trivial. It doesn't mean anything. It gives me no information. It's unnecessary. I don't care about it. It's not a useful solution to me, right? The most useless solution to this equation is when C1 is 0, C2 is 0, Cn minus 1 is 0, Cn is 0. When all of these coefficients are 0, I obviously will get out 0, and it tells me nothing about my system, right? It's basically me looking at the origin. It doesn't do anything for me, right? So the solutions to this that I'm interested in are the times when I have C1 is 1, C2 is negative 2/3, this one is 1/2, right? When I have actual coefficients that are able to allow me to add these functions together and get 0 out. That's interesting. I can analyze that solution. I can use that solution for things. Trivial solution is just multiply everything by 0 to get 0 out, right? It's trivial. It's not informative at all. Okay. So again, the trivial solution is when all of these coefficients are equal to 0. So remember, for linear independence, C1, C2, up through Cn, these are all constant coefficients. They're all real valued numbers. They are not functions in this case, right? That's only when we're dealing with the differential equation. So these are all constants, okay? If something is not linearly independent, then it is linearly dependent, okay? So one of the interesting things that come out of this, right, is that if this is not linearly independent, right, if the only way to add these things together is if all of these constants are 0, right, that means linearly independent. Linearly dependent means I can take one of these functions and I can move it to the other side of the equation, and that means that one of these functions, any of these functions actually, can be rewritten as a linear combination of all of the other functions. That's what it means to be linearly dependent. Very, very important to know when something is linearly dependent and linearly independent, right? So let's go ahead and do an example, right? So consider y equals to 2x, y equals 6e to the x, and y equals x. These three functions are linearly independent, since none of the functions here can be rewritten as a linear combination of the others. There's no way for me to add e to the 2x and 6e to the x together in order to get x. So no matter what, a constant multiple of this plus a constant multiple of this will always be some sort of e to the 2x plus e to the x. Never, ever, ever can I add these together and get just a single x function out, right? So these are linearly independent. Same thing with this. There's no way for me to add this plus x together in a way to create e to the 2x, right? Same thing with this function and this function, e to the 2x plus x times any multiple of x, right? 3e to the 2x minus 17 over 5x will never be any form of a constant multiple of e to the x. Never, right? So there's no way for me to combine any of these together to get one of the other ones, right? So they are linearly independent of each other, right? Or an easier way of saying that is that the only way for this equation where I'm adding all of them together and multiplying them times some constant multiple, trying to get them to add up to 0, the only way for that to work is if all of these coefficients are 0, right? If I turn this into 0 plus 0 plus 0, I'll get 0 out. But there's no other way for me to get out 0. Therefore, they are linearly independent. Let's take an example of something that is linearly dependent. Okay, so this is something that's common to you guys, which is why I chose it as our example. Through experience, that I can add these two things together in a way to make this last one. I can actually combine these two together in a way to make this one, and I can add these two together in a way to make this one. They're all interconnected, right? That's the Pythagorean theorem. It's one of the first identities that you learn from trigonometry, right? Which is why I chose this. It's a super easy one, okay? It's linearly independent because I can add these in a way to get 1. There's also a way for me to add all of these together to get out 0, okay? So when we think of linear combinations, typically when I think of linear combinations, I think of, can I add 2 of these together in a way to make the third? That's how I think of linear combinations. But the formal definition is that you add all of these together in a way to get 0, right? They're equivalent ways of looking at the same thing, right? So I know that if I add sine squared x plus cosine squared x, I'll always get 1, right? Pythagorean identity. This is one of the fundamental identities of trigonometry, okay? So using the definition of linear independence, right? A constant multiple of sine squared x plus a constant multiple of cosine squared x plus a constant multiple of 1 equals 0 has more than just the trivial solution, okay? So in fact, if these are 1 and this is -1, I'll get 1 plus -1, which will give me 0. It is a solution that satisfies this equation that is not the trivial solution, okay? And notice also that linear independence does not have to do with the function I'm using, okay? So as we showed here, these functions are linearly independent, but they are not linear functions. This is not a line, this is not a line, this one is, but these two functions are curves, right? But their combination forms a linear combination, right? A linearly independent linear combination. So linear independence and linear combinations has nothing to do with actually being linear functions or not, right? It's the way that they are combined together, right? Whether I can combine them together linearly to create one of the ones that is already there. That's what we mean by linear combinations and linear dependence or linear independence, right? So there's another way of computing linear independence, right? So again, not to talk too much about linear algebra, right? But the main idea of linear algebra is this thing, right? Knowing when and how to figure out whether or not something is a linearly independent or linearly dependent. It's a very, like I said, it's a very big deal, right? So for this class, we have what's called the Wronskian, right? Especially since we're dealing with functions, right? Linear algebra, you're dealing with all objects, vectors, functions, all kinds of things, right? Here we're doing really just focusing on functions. So we have a way of testing for linear independence by computing what's called the Wronskian, okay? So for the Wronskian, I'm basically going to plug in several functions, all the functions I'm interested in, into this Wronskian. And what I'm doing is I'm basically going to make a matrix, okay? So I'm going to put all of my functions in the first row. In the second row, I'm going to differentiate all of my functions, okay? In the next row, I'm going to write the second derivative, and then the third derivative, and the fourth derivative, so forth and so forth and so forth, all the way until the n minus 1th derivative. So this matrix that I have is now square. I have n elements here, right? 1, 2, 3, 4, to n. And then I have n elements down. 1, we can call this 1, right? First derivative is 2. Second derivative is the third element. So that means that this would be the nth element, right? I have n minus 1 elements plus 1 more gives me n elements, right? Because I'm starting here. So I do this until I have a square matrix, right? So if I have 5 elements in here, I'm going to put in the fourth derivative, right? That'll give me 5. The regular function plus its 4 derivatives is 5 elements. These lines here, okay, in case you don't remember, straight lines mean not a matrix, but the determinant. This is a function. I'm plugging these things in and I'm plugging it into a function. So from Calculus 3, you have learned determinant. I don't know, actually I know how you've learned determinant. If you took in a linear algebra course, you know several methods of finding the determinant. You can use any of those methods in this class, okay? Any linear algebra methods you know, you are allowed to use if you are taking linear algebra concurrently or have already taken linear algebra. That's fine. I'm fine with linear algebra. You do it whenever you can, okay? I love that class. It's wonderful. I love this class too. You guys are great. Anyways, you need to find the determinant, right? So from Calculus 3, you have your cofactor expansion method where you are going down a row. Again, if you're in linear algebra, you can use any of the several methods that you know. I'm fine with it. Just show your work, right? So I can see what's happening. Now, if the determinant of this matrix that you found is not 0, then you are linearly independent, okay? So as long as the Wronskian, which is the determinant of this matrix that you have with its functions and its n minus 1th derivatives, right? If the determinant of this matrix is non-zero, your functions are linearly independent. If this determinant is 0, then your functions are linearly dependent, and there's a way for you to create a linear combination of one of the functions out of all of the remaining functions, right? So let's do an example. Let's do our previous example because we already know that these are linearly dependent, which means that my Wronskian should be 0 or non-zero. You guessed it. It should be 0, okay? If the Wronskian comes out to be 0, they're linearly dependent, okay? So I'm doing quite a bit of work in this example, but not a lot. So ideally, you are pausing and doing some work on the side as we go through this, right? So I need to plug in my functions. It really does not matter what order I put them in. It could be 1, sine squared, cosine squared. It could be sine squared, cosine squared, 1. It really does not matter the order. It all come out eventually the same, right? So here I am putting it in order, right? Because that's the order that I put my functions into my Wronskian function. So I have sine squared x, cosine squared, and 1. And then I'm just going to start finding the derivatives, right? So sine squared, you're going to use chain rule, right? 2 sine times cosine, right? Here I'm going to get 2 cosine times negative sine, right? 1 is going to go to 0, right? And then for my next derivative, I'm going to do the product rule here, and the product rule here, 0 goes to 0, right? So again, maybe do some math on the side because I don't feel like doing this. But you get 2 cosine plus 2 sine cosine. Sine? It doesn't matter. Do it on the side, right? I did all this work on the side as well. So you should verify on your own that these are the second derivatives, right? So when I go through and I do my determinant, there's several methods, right? So if you go through the determinant section in my linear algebra method, in my linear algebra video series, you can go ahead and learn quite a few methods if you'd like to be more robust in your method of finding determinants, right? So I have a method that I like. I'm not going to do it here. I'm going to stick to what most of you guys are probably familiar with. So I'm just going to do my cofactor expansion. Obviously, going down this row is the easiest one because there's lots of zeros. So remember, it goes plus minus plus, okay? You get rid of this row, you get rid of this column, and you multiply 1 times the value that's here times the determinant of the submatrix that's left, right? So it's a 2 by 2 submatrix, so that's really easy. So I'm going to multiply this times this and subtract from that the product of this times this, okay? So again, you might want to do that on the side, maybe pause this video, find that work on the side, and then we'll come back and compare our answers, right? So this times that, and this times this, right? So you can kind of almost see already that they are identical, right? There's just kind of a sign switch that happens here. So we'll go ahead and do this. So this is the first product, right? 2 sine x cosine x times 2 sine squared minus 2 cosine squared, right? That's the first product. In the second product, we're going to subtract this one times that one. So that basically just turns that into a plus times that, okay? There we go. All right, so plus 2 cosine sine times this one, right? Now, if we expand this, right, so this times this term, this times that term, this times this term, and this times that term, we'll get this long thing, lots of 4s everywhere, right? But you can see here that we have a lot of things that are the same. So 4 sine 3 cosine, negative 4 sine 3 cosine. So those two ends go away. And for the ones in the middle, I got cosine is cubed, 1 sine, and 1 plus and 1 minus. So these two ends cancel, and these two middle ones cancel, and you just get 0. Okay. So now you might be saying, well, Professor Williams, on an exam, can't I just be like, hey, I know that this is 0 because like it's this times that, it's the same thing as this times that, but it's a different sign, and I'm moving it. Just show me the work, okay? I want to just make sure that you know what you're doing, that you're not copying an answer somewhere. Show as much work as possible if you want full credits. I would take off a point if you went from here straight to telling me that the answer is 0. I'm definitely going to take off 1 to 2 points. Make sure you're showing everything, okay? I want to make sure you know what's going on, right? Basically, I'm not there to observe you, so make sure everything is clear, okay? Therefore, since the determinant is 0, these three functions are linearly dependent, which we already knew from our previous exploration above over here.